Guys, this is your channel. I'm not seeing any comments. I saw one from Tafazwa. Whether you are enjoying or you are not enjoying, let comments come. We want to tailor make this channel for you so that you benefit most. Thank you. Welcome to our 8th video on electronics 1, and in this video we are going to look at clampers. In the previous video we looked at clippers, and as usual, Motion Marufu is my name. Guys, I need your comments, whether you are liking or you are not liking. Keep comments coming. We want to make sure that this channel is tailor-made for you. I need to improve. I cannot be doing everything according to your liking. So let comments come in and we will respond and shape the channel into the one that you like. If there are any videos which you think must be given a priority, because we are still to cover BJT, we are still to cover JFET, MOSFET, op-amps, power electronics. If you think there are some topics which you think need a priority, let comments do the talking. Otherwise, let's enjoy clippers. We've got only 4 objectives for this presentation, and the first one is you must be able to, by the end of this presentation, define clamper with the aid of examples, and also number 2, describe with the aid of circuit diagram the various types of clampers. As you can see, circuit diagram, circuit diagram, circuit diagram, circuit diagram. That's all about electronics. Then number 3, you must be able to perform some circuit clamper calculations. Then last but not least, you must be able to explain with the able suitable diagrams practical applications of clampers. Guys, I don't know what you will enjoy if you are not enjoying electronics. Electronics must be enjoyed. Clampers. Introduction. We start by defining what exactly is a clamper, and I know you've been wondering what this kind of animal is. This is simply a circuit. We know when we are in electronics, we talk about circuits, and more circuits. And it is used to convert a waveform of any shape into another waveform whose positive or negative or both polarities are maintained at some constant reference value, and the normally used reference value is the 0 reference value. Because the output cannot rise above that reference value, which normally is the 0 reference value, it is said to be clamped at or to that level. If a signal is passed through a coupling capacitor, we know a capacitor blocks DC. We say it loses its DC component. A clamper then is used to restore that DC, or it is used to reintroduce a new one to that particular signal. And for this reason, clampers are also known as DC restorers or DC inserters, since they insert or restore the DC that would have been lost. Please take note that a clamper is basically made up of a diode, a capacitor, and a resistor. The value of R and C, actually if we multiply R and C, we get what we call tau, which is time constant. And the value of R and C are chosen so that the time constant tau is very, very large. And this enables the voltage across the capacitor to remain almost constant when the input is being fed, and also when the capacitor is not charging. In other words, when the capacitor is discharging, the voltage across it must almost remain fairly constant. That basically is what we mean by a clamper circuit. Types of clampers. We've got basically 2 types of clampers, a positive clamper and negative clamper, just as we have got 2 polarities, positive and negative. And we said a clamper adds a negative or positive DC voltage to a signal of any shape applied to its input. What does a positive clamper do? it shifts the entire signal so that it is above a DC reference value, and the normally used different DC reference value is 0 volts. That is to say, positive clamper shifts the input waveform so that its negative peak is approximately or equal to the DC reference voltage. What does a negative clamper do? It does the opposite of what a positive clamper does. It shifts the entire input signal below a DC reference voltage so that the positive peak of the input signal is approximately equal to the DC reference voltage. Don't worry, the moment we introduce the block diagram in the next slide, it's going to be very, very clear. Figure 1.1 is showing the operation of a positive clamper, and it's in block diagram form since there are no discrete components. And we are saying a clamper shifts the input signal. This is our input signal without distorting the waveform. And we are saying this is the input, this is the input signal, the output signal, and this is our positive clamper, the block diagram. And we are saying, please take note of the following. From there to there, from the positive peak to the negative peak, we call it peak to peak. This PP means 20 volts peak to peak voltage. But from 0 to the maximum value, to the maximum positive value, and also from 0 to the minimum to the maximum negative value, we call it peak. So peak to peak is equal to 2 multiplied by peak voltage. And what has happened to the output? This is our 0 reference value. So we have shifted this signal so that its negative peak voltage or its maximum negative value is equal to the 0 reference voltage. And our output still has the same peak to peak voltage, which is 20 volts peak to peak. So there's no distortion. We've maintained our peak to peak value. That's one of the characteristics of a clamper. It maintains the same peak to peak value. It doesn't clip off as what a clipper does. So we are saying a positive clipper shifts its input waveform so that the negative peak, this is the negative peak, is approximately equal. This is our 0 reference, so our negative peak is sitting on the 0 reference voltage. An explanation for you, we are saying a positive clamper shifts the input waveform so that the negative peak of that particular waveform is or sits on the DC reference voltage of the clamper, which according to our block diagram is 0 volts. And this shows what happens when a 20 volts peak-to-peak sine wave is applied to a positive clamper having a reference voltage of 0 volts. Our input has got a 20 volts peak-to-peak, but our output has got a peak value of plus 20 volts. And its other peak value is 0 volts, and it becomes our negative peak, since the negative peak of the input will sit on the 0 reference voltage, which is 0. So we are saying, what is the clamper done to our 20 volts peak to peak AC input? We are saying it shifted the entire waveform so that its minus V peak is approximately equal to 0 volts. Negative clamper block diagram. This block diagram is representing negative clamper. This is our input signal generator. From there, it is going to be fed to the clamper circuit. Then from the clamper circuit, we've got our output signal, and as you can see, something has happened. So what is happening? We are saying a negative clamper, or we've said rather a negative clamper shifts the input signal so that its positive peak, this is the positive peak, mind you, these are negative peaks. So this must be equal to the DC reference voltage, and our DC reference voltage is 0 volts. So this positive peak now sits on the 0 reference voltage. So we are saying when a 20 volts peak to peak, which is our input signal, is applied to a negative clamper, this block diagram, and its reference voltage is 0 volts, we are saying this clamper output has a peak value. Its maximum peak value of this sine wave input is now 0 volts and minus 20. So we are maintaining the peak-to-peak voltage from 0 to minus 20, which is 20 volts, and the input was 20 volts peak to peak. So the peak-to-peak value is being maintained. It is showing that there is no distortion to the input waveform. So we are saying a negative clamper shifts the entire waveform so that its positive peak is approximately equal to the DC reference voltage of 0 volts in this case. So easy. Let me go through again the operation of a negative clamper, and we are saying it shifts the input waveform so that the positive peak of the input is equal to the 0 DC reference voltage. And according to our figure, a 20 volts peak-to-peak sine wave is applied to a negative clamper and its reference voltage is equal to 0. This means that the positive peak must be equal to 0 volts. So the output is a peak value of 0 volts, which is the positive peak, and its negative peak is minus 20 volts, therefore maintaining the peak-to-peak of the input waveform. In other words, we have shifted, or it has shifted the entire waveform so that its positive peak sits on the 0 DC reference voltage. In electronics, we have got what we call average voltage, and in short, it is called V subscript of shift. And we are saying a clamper shifts the average voltage of the input. And let's go through our literature and see what does that mean. We are saying our input is not rectified and it has got the average voltage that falls between the positive and negative voltage values. We are saying if we've got an AC signal with a peak of 10 and a negative peak of 10, we are saying its average value is equal to 0. But when we shift the input signal, the average value changes. And we'll look at our examples. The output of the clamper had 2 peaks, 0 and plus. If we find the average of the two, we get a plus 10 volts. But the average voltage of the input was plus 10 and minus 10, giving us 0. So if we were to measure the average voltage, we would get a reading of 10 volts, that is at the output of the clamper. Also for our negative clamper, we would get a minus 10 average voltage, which is also referred to as VDC. Please take note, VAV is the same as VDC. Why minus? Because it has got 2 peaks, 0 volts and minus 20. If we add the 2 and divide by 2, we get minus 10 average voltage or VDC. So we have got an interesting point that we can make, that while the average voltage of a waveform changes when it goes through the clamper, please take note that we maintain the peak-to-peak value, or the two maintained their peaks, or the peak value of the input volts of 20 volts peak-to-peak value was maintained at the output. So we didn't change the peak-to-peak value of the original signal. We only changed the average value, which is the VDC. When I want to see how our capacitor charges and discharges due to our input signal, we are saying this is our capacitor, this is the negative, this is the positive. TC stands for time constant and it is 5 tau. Tau is RC. I think you remember from the previous, from an earlier slide. This is the dynamic resistance of the diode times the capacitor. value. So we are saying our capacitor charges when the diode is forward biased, so it charges in this direction. Why? Because our input is positive, so this diode is going to be forward biased, hence it charges in this way. This is our load resistor. When the capacitor is charged in this way, it is when it discharges in this direction through the load. Please take note, the capacitor discharges through the load, and normally it discharges when the input is negative. So we are saying the clamper is similar in construction to a shunt clipper. Why? Because the two are in parallel. The difference is the added capacitor in the clamper. The difference is between a clamper and a clipper you are given here. So we are saying the discharge time of the capacitor is also 5 tau, which is where our tau is equal to resistance of the load resistor times the capacitance of C1. And we said this time constant must be greater than the time period of the input waveform, so that we maintain the voltage across the capacitor when it is discharging to a fairly constant value. The difference between a negative clamper and a positive clamper is in the direction of the diode, which also determines the orientation of the capacitor. And this is a negative clamper. In other words, it shifts the input waveform so that its positive peak sits on the reference voltage, which in our case is the zero reference voltage. So we are saying this is the way how the capacitor is connected. For a negative clamper, this becomes the positive, this becomes the negative. So we say negative voltage developed across this capacitor because of the way how it is connected. So we are saying when this diode is forward biased, it is going to charge this capacitor in this direction. So when this capacitor is charged in this direction, it will happen that when the input becomes negative, this capacitor is going to be reverse biased, and when this capacitor is reverse biased, it is the capacitor that now has the turn to discharge, and it is going to discharge through this resistor RL. So we are saying this is a negative clamper. Let me repeat, this is a negative clamper. Why? Because the positive peak is now almost equal to the zero reference value. So you must be able to draw and to describe the operation of this negative clamper. Please, you emphasize the following: that this capacitor charges when the input is positive and it discharges when the input is negative. That the peak-to-peak value does not change, but it is the average voltage that is changed. Center tape wave rectifier. Center tape is coming from the negative peak is now equal to the 2 minus the peak-to-peak value of the input. A positive clamper. We've just dealt with a negative clamper, and as you can see, the voltage has been fixed to a value above the reference. For a negative, it was below the reference, in that the negative peak is now equal to the zero reference value, while the peak-to-peak voltage of the input is maintained. So we are saying we have reversed the diode, and our capacitor is now connected like this. This is the negative, this is the positive. So we say this is a positive voltage as indicated on the diagram. And we are saying since the diode is returned to ground, the circuit shifts the input waveform until the negative peak is equal to the 0 volts reference value. Please take note, when reverse biasing the diode, the capacitor, if polarized, must also be reverse biased as we have done. The positive side of the polarized capacitor must always be connected to the more positive of voltage. In a negative clamper, the positive terminal of the capacitor is connected to the signal source. We saw that the anode was connected to the signal source. In a positive clamper like this, the positive side of the capacitor is connected to the output. For the negative clamper, it was totally different. But there is a quick and easy memory trick for determining what type of clamper you are dealing with. And please take note, if the diode is pointing up, that is away from the ground, it is a positive clamper. And if the diode is pointing down towards the ground, it is a negative clamper. Please take note, this is a summary of a positive and a negative clamper. It must stick into your mind so that you're able to draw. We want to see how the capacitor charges in a positive clamper, and we are saying this is our circuit diagram. When the diode is facing up, it is a positive clamper. Please take note of that important point. So we are saying when the input is positive, this diode is going to be off, so this capacitor is going to charge during the negative half cycle, and it is going to charge up to this value. But there is a difference in the way how this capacitor charges during the first cycle and also during the second cycle onwards. So we are saying when the input is negative, this diode is going to forward biased and is going to conduct in this way, charging the capacitor. Please take note that this polarity is the same as this polarity, since this is an ideal diode. It behaves as a wire, just like what happens in resistors. Check your Kirchhoff's voltage law. So our capacitor is going to charge in this direction to this value, which according to our Kirchhoff's voltage law is negative, and this one is positive. Potential rise and potential drop as long as we are going in this direction. So we are saying the low impedance forward bias diode completes the current path. Yes, it completes the current path in this direction, thereby allowing the capacitor to rise to the peak input voltage of the negative half cycle. And we are saying after the input voltage is reached higher than after the voltage across the capacitor is reached higher than the input voltage, our diode is going to be reverse biased. Please check your Kirchhoff's voltage law. This voltage, for this diode to be reverse biased, it has to be higher than this, so that this will be at a higher potential than this, for this diode to be reverse biased. And when that happens, the capacitor starts to discharge through the load resistor RL. And how does it discharge? It discharges in this direction, in the opposite direction in which it was charging. We'll confirm that in the next slide. Let's go. We are now looking at the way how the capacitor discharges. As I said, it's now discharging in this direction, in a clockwise direction, but it charged in an anti-clockwise direction, and it discharges through the load. It discharges through the load. And if the diode is now reverse biased because of this positive voltage to which the cathode is connected, hence it is reverse biased, which means it is off, it is behaving like an open switch. Please take note that in the first charging curve, the capacitor must charge first before it discharges. The capacitor must charge first before it discharges. Please take note of that important point, otherwise you get confused. So we are saying the capacitor is now, we know the property of a capacitor is to store charge. So this is a polarized capacitor. It's got a negative and a positive end. It has now been charged to plus 5 volts, but its output now, because its negative peak is now equal to the zero reference voltage, it's now producing an output across the load of 0 to 10 volts, which is the same as to peak, which is 10 volts. How does that happen when it is charged to 5 volts? This happens because we now have got this half cycle. This half cycle plus this voltage, this half cycle is 5 volts, and this voltage across the capacitor is now 5 volts. So we are saying the voltage across the load is going to be 10 volts. That will be the peak value. So in other words, we are maintaining a peak-to-peak value of 10 volts, whereby the peak value is 0 and the other peak value is 10 volts. So this is the way how the capacitor discharged to discharge in this direction. The last slide in this presentation is comparing clippers and clampers, and it's very simple. You can go that on your own. The components used in a clipper are diodes and resistors. Well, in a clamper we use diodes, capacitors, as well as resistors. The function of the clipper is to remove part of the input. Then the function of the clamper is to add a DC shift to the input. The frequency is not important in clippers, as a capacitor is not used, because we know capacitors and inductors, they offer some reactance which depends on F to the flow of a sinusoidal input. But on a clamper, the value of the capacitor is important because RC gives us tau, so the value of the capacitor is chosen depending on the input frequency. Then applications, the clippers are used in wave shaping circuits, while clampers are used as voltage multipliers. So that is it in as far as clampers are concerned. The next time when we meet, we'll be talking of voltage multipliers: half wave, voltage doubler, full wave, voltage doubler, and voltage tripler. That's what we'll be looking at in our next video presentation. Until then, don't forget to mask up, to wash your hands under running water for more than 20 seconds, and also be vaccinated against COVID-19. Until then, we have come to the end of the 7th presentation. Next time when we meet, we'll be talking about voltage multipliers. We'll be talking about half-wave voltage doubler, full-wave voltage doubler, voltage tripler, to mention but just a few. Guys, if you are enjoying, show that by hitting the subscribe button. Until then, take care of yourself. Remember, COVID-19 is there. Wash your hands, mask up, and be vaccinated. It's Motion Marufu.